Hi everyone, welcome to the 203 eCHO episode. I'm very excited to be here today, but I'm not here. Actually, this is a recording version, so I will not probably be able to answer your question, but please reach out to the Slack channel anytime, and let's get into it. Today, I'm with Tarazi. He's a software engineer also at Isovalent.
Hello, everyone.
And we're gonna talk about funny things. Let me share the news of today. So you can check all the notes on HackMD website on eCHO Live. And today we have some news. So the next episode is gonna be with Duffy. It's gonna be about the AI lab, a new branded lab. That sounds very exciting. I didn't test it yet, but I'm very excited about it. If you have any issue or concerns or questions, please reach out to the Slack channel. And maybe you already saw it, but CiliumCon schedule is live, so you can register. You can check all the agenda. It's the afternoon this time, so on the Monday on collocated events. So I will be there. So I would be very happy to talk with you. I will be at the booth, Cilium booth all day. So see you there, hopefully. And so yeah, today we're going to talk about eBPF Hookpoint Gotchas. We gave this talk actually at FOSDEB 2 weeks ago, and we are doing not another version, but we're doing new version of it today. And I hope you're going to find that very cool and interesting because we learned a ton while preparing this talk, right? So let's get into it. So we're going to talk about eBPF Hookpoint Gotchas, but most specifically, we're going to talk about why the program fires in unexpected way. So as a disclaimer, we're not going to talk about like everything or cover everything. It's not going to be exhaustive, so you know. Let me do that properly. Okay. So we're going to talk about tracing Hookpoints overview, what it is, and have just a better understanding. Some generic gotchas, the kernel versions, different architecture, performance. We're going to talk more about uprobe dynamic link gotchas, some inlining, funny ones, and Chris will talk about the nested execution gotchas. So let's go.
All right, so we're going to look at kprobes, uprobes, fprobes, and tracepoints mostly in this talk. And we'll start with kprobes and uprobes. So they're very similar, but they differ only in that kprobes are meant for kernel functions and uprobes are for user space functions. Both can be attached at the function entry offset or function exit offset. And they don't have any stability guarantees in the kernel between kernel versions. So like, for example, a function may change between kernel versions and you'll be required to rewrite the hook program. Both kprobes and uprobes have existed for a long time in the kernel. They're the most ubiquitous and easiest to use because they're quite dynamic. And fprobes are similar to kprobes, but they differ in a few ways. They use the ftrace infrastructure, which makes them more efficient, especially if kprobes are not running as optimized. And we will touch on that later in the talk. Fprobes can be attached on the function entry and exit, but not the offset. And that's the main difference with them between the kprobe and uprobe. And then lastly, we have the trace points, which are statically defined points in the kernel and meant for stability. They work by injecting 5 bytes of no-ops at the trace point entrance, and then those are later rewritten into jumps to your trace point program. Okay, so now we have the overview. Let's look at some performance numbers. Okay, so here's a quick benchmark a simple benchmark that shows the difference between the hook point types. So the most relevant number here is you have the overhead percentage, and that gives us like the high level idea of the performance cost when using these hook points. Keep in mind that the amount of overhead is dependent on like on whether the function probed is in the hot path or not. So it's not a direct translation to like overall system slowdown. Yeah, so as you can see, trace points have the highest performance because, as we mentioned, they're statically defined. F probes follow them, and then K probes are last. We sort of mentioned already how they're dynamic, so and they use the interrupt-based implementation, and we will learn why that's slow and can cause some issues. All right. You're muted, Donia.
Yeah. So let's move to the first gotcha, the kernel versions. So on most of the infrastructure out there, there are different kernel versions running, but how do you actually write an eBPF program running on different kernel versions? So fprobes and kprobes have no stability guarantee. So for example, if you have a new release, they can change, all the internal function can change. And function, like when you're refactoring, a function can be renamed, removed, inline, and it will fail to attach because symbol will not be found. But we'll talk about that later. We have also function argument that can change. Typically struct fields, like if you're moving them or adding new ones, and it's going to read the wrong arguments and then garbage data. So some alternatives to that is to use tracepoints. We mentioned it already, but it's more reliable if possible. It's statically defined, so it's actually developed by the kernel developers, so it's more static in that way. It has a guaranteed stable ABI, and arguments are documented and maintained, and you can actually find them on the syskernel tracing file. I have a question for you in the chat. So what if there is no trace point for the function that you want to cover? What are your options? So you have response A, you can hardcode the function name and hope it doesn't change. Response B, write separate BPF programs for each kernel version. That can be daunting. C, use core with BTF for automatic adaptation, or D, abandon eBPF and use kernel module instead. I'm curious to see your response in the chat. So yeah, it's response C, use core with BTF for automatic adaptation. So what is core and BTF? So core is for compile once, run everywhere. And it means that BPF programs adapt to kernel at load time. BTF for BPF type format or type information embedded in the kernel about your program. So you can, for example, if you are changing the struct fields again, it's going to adjust the offset storing all this information automatically. So it will adapt to multiple kernel versions no matter what. Let's move to the second gotcha about architectures. So kprobes have some unfriendly interface that's actually known, and the context passed to a kprobe in the struct ptregs is a struct representing registers, and it stores the function parameters. But if you're using different architectures, you're going to use different registers. So the way you're going to access the register and all this information is different. So you have some alternative to that. Again, you can use other hook points, fprob or trace points, no trace points actually. And libBPF, which is a library, provides helper for access. So it's going to be agnostic from the type of architecture that you have, and you can just use the wrapper to access the register. So that's an option in your program when you're developing for different architectures. Sorry. Okay, let's move to the gotcha number 3, dynamic links. Here is simple library with libmath. It has one function add, taking 2 parameters and doing an addition. The main program is loading the library, attaching the library, and calling the add function. After compilation of the library and the main program, we probe to the add function using BPF trace tool, and we can check the symbol table, and we see that for the add function, we have an offset, and the probe is going to be attached there. So let's see if we run the program. What is the output? So the program is resulting 5, doing the addition, and BPF trace will actually add here the line uprobe add to 3, meaning that it actually did the job, add had been called, and the probe is firing the call to the function. Great, we're happy with that. Now we're going to update the library. We're going to insert new function, subtract and multiply, and we're going to see what happened after compilation of the library and the main program. So we are running the program, the main one, but what's happening on the BPF trace output? I'm asking you, what's going to happen? So do you think that response A, we're going to see again the add function call? Do you think that we're going to see the subtract? Nothing is going to happen, probe silently stops working, or none of the above? Please put it in chat. So the response is C. In fact, it's not going to fire and it will stop firing. So let's see why. In the symbol table after the update, we're going to have new offset for the new function because they have been inserted. So the uprobe is still attached to the previous offset, which is now corresponding to an undefined point in the memory, meaning that the uprobe you should be reattached to the new offset to fire again. So let's see that. So no, we're not going to see that, sorry. But in fact, what you can do to bypass this, especially in production, because even library updates are rare, it can happen for security patches, security reasons, and your monitoring may silently break without warning. You can either use monitor for file changes. There is a tool called iNotify-Wait to do it. Or you can use a supervisor program that monitors updates to the relevant shared libraries to reattach to your props after updates. And let's move to the next gotcha about inlining. I want to ask you first if you know what is inlining. I know it's all time, but inlining is an optimization where a function call is replaced with the actual code of the function itself at the point of call. We're going to see more in details. We have, again, a simple add function called in a main program, only if the given parameter is actually above 5, greater than 5. And then it will just do the addition here and print the result. After compilation with no optimization using GCC, we can see that we have the symbol of the function add, and we have big T. It means that it's global and external symbol, and we have the offset corresponding. And we are using the tool LM to do it. Then we're going to compile with the level of optimization O2. And we can see that we have also the same symbol. So it should be okay, right? I should be able to attach to add function in both cases without and with optimization. So let's see actually here. I'm going to run the program that I just showed you and attach to it first. So I'm using BPF trace to attach to add, and I'm going to launch the program with 0 and then with 10 value as input. And we can see that we have the function that is called. So we're happy with that, right? The probe fired because my value was greater than 5. Then I'm gonna trace to the optimized program. And again, I'm gonna launch with value 0. Okay, nothing is happening here, right? And then with value 10, and nothing is happening again. So what's happening? What's going on, right? So let's see. We are having, like, here, this is the disassembled binary. BPF trace is probing to symbol and then convert to offset where the function is defined. And in the case of no optimization, as you can see on that side, because it's branching, we can see here the BL. BPF trace is probing on the offset corresponding to the actual instruction that will be executed. So in the case of optimization, what's happening? We can see that we don't have the BL, we have directly the instruction, because we have what we call a selective inlining. The instruction are replaced, therefore the function definition offset will never be reached during the execution. So you should then probe on the offset on the actual instruction of the caller. So here, this is the offset we want to attach to. And let's see if we attach to the offset. So I'm going to use another tool called perf. And I'm going to use the offset and launch with 0 value. Nothing happened. Let's see. Yeah, nothing happened. Let's do it with 10. Is capture and wrote one sample. Can we see it? Yeah, we can see it. Here, we can see that the inline add function had been called when we are probing to the proper offset. Good. So we saw that the problem was that the symbol exists in the binary. It was visible using NM, but the compiler inlined the function into the caller. uprob is attached on symbol, but it never fires, and the execution instruction inline are in the caller, or inline in the caller. So how to detect selective inlining? You can show this assembly code using object dump or LLVM dwarf dump. This is 2 tools that can be used. And you can check if the function is inline. As we saw, like the BL, meaning that there is a branching, there is a real call. So that's going to be okay. There is no selective inlining. And if you see the instruction directly and there is no BL to the actual call to the function, it means that selective inlining has been applied. So what are the solutions? You can use uprob or kprobe with offset. You can look inside the caller function disassembly. You can find the instruction that does the work, add for addition. You can calculate the offset using the instruct address minus the function address to have a relative offset. And it will fire when the execution reaches that exact instruction. There are some caveats. In fact, if you have multiple call sites, you should have multiple probes. Offset can change after recompilation, so you should be careful about that. And different compiler version will give probably different offset too. So there is no practical solution here for production, but it can be useful for debugging. Okay, let's move on to the next gotcha about inlining again. And we're gonna look at a code. So here we have a function named allocate resource, and it's a simple function that validates input, do some computation, and returns the results. Nothing fancy, right? So you might think attaching to a prob here could be straightforward. I have a question again for you. How many symbols does this generate when compiling with the following command? So we are using O2. Response A1, response B2, response C10, response C, what the hell are symbols? I'm sorry for you. You can drop in the chat again. So the response is 2. We can see here with the nm comment that we have one external symbol for allocate resource function, and we have a new one that is not exposed here with a suffix part 0. So let's see what is that. It is actually called partial inlining, and we're going to see what GCC does. So when you launch GCC with O2, it's gonna activate partial inlining, and it will split function based on execution patterns. So you're gonna have fast and slow path. Fast can be, for example, for validation check, and it's gonna stay in small wrapper. And slow path are actually loops, string formatting, IO operation, and they're gonna get extracted to part 0 and other part functions. And you can see that before we had one monolithic function that we wrote, and after GCC, we have at one offset allocate resource, and then a jump to the allocate resource part 0 with all the for loop doing the actual computation. But why does GCC do this? So there are several reasons, but having smaller fast code like hot part fits better in instruction cache. It's gonna have better branch prediction, and the CPU expect the fast path. And it also reduces register pressure with the call slow path variables, so they don't pollute the hot path. So everything is just optimization to go faster and have like a very fast like CPU execution. Let's have a quick demo again. Okay. So I'm gonna launch actually the program that I just showed you. I'm gonna BPF trace on allocate resource. We can see that here. And with no partial, we have no optimization. We have the probe. We are happy with that. Then I'm gonna probe to the one with the optimization. And you can see that nothing is happening here when I actually probe to allocate resource. Let's see if I'm doing it on the part 0, and I'm gonna launch again the program. And you can see that I have actually my probe firing. So we've seen that we missed some events if we don't probe to all the different parts and only to the main one if we are using optimization, which is often the case. And we saw that it was silent in the case of allocate resource, and we had actual allocation showing here when probing to resource part 0. This is called partial inlining, and there are some alternatives to that. You can use trace points, but you might encounter the case where you don't have one-on-one translation. You can, for uprob, you can use no partial inlining option here, directly mentioning it. And for kprob, because you cannot recompile production, like the kernel for production, it's not common. You should identify symbol using tools, and for that, you can check for suffix symbols, verify with dwarf, and or see source mapping with object dump, like we've done previously. That was all we have for inlining. Let's move to the next gotcha.
All right, let's look at mixed executions. So here we have this output from BPF tool, and you will see an fprobe, a kprobe, and a tracepoint program. And then there's something interesting there at the end to the right. Any ideas what recursion miss represents? Leave your answer of what you think in the chat. It is the number of times a BPF program fails to execute due to missing kernel function, or B, how many times recursion protection prevented a program from running again. A C, a count of recursive function calls that the BPF verifier rejected, or D, number of missed hardware events due to recursion in the perf subsystem. So it's B, number of times recursion prevented from running again because it was already executing. So as we saw in the BPF tool output, your tracing programs can, maybe surprisingly to you, miss executions. So in the case that you're depending on these probes for security or observability, this can be a bit of a challenge. So like, for example, you're on the security team, you're interested in monitoring file operations on your infrastructure, and you're using BPF to like monitor all file open events, for example. and you might be expecting like 1,000 events, say, from your metrics, but then in your audit logs, you only see like 900 events. Maybe you're debugging some kernel internals and you're tracing a hot function, and like the bug occurred like when the probe missed an execution. So you actually missed the stack trace that you would need to do the debugging. So those are like a few examples of how execution, like missed executions, can impact you. So yeah, it might be surprising to learn that tracing hook points are not 100% reliable. So let's dig into these different the different ways that these hook points, such as kprobes and fprobes and trace points, can miss executions. And then we'll learn how and why, and then we'll discuss some workarounds. Okay, so probes generally have two different places in the kernel where it can miss executing them. So one is when the probe re-enters or recurses itself before completing the first execution. And then the second way is if there's any other execution of another BPF program. So crucially, these misses only happen if the execution occurs on the same CPU. If it is a different CPU, it's a new context, and the probe will execute without missing and without a problem. Okay, so let's kind of look at what recursion looks like. So see in example 1 here, we have kprobe on open at 2. It calls print k. Print k takes a print k lock. At the same time, we have a trace point on contention begin function. When contention occurs on the print k lock, then the trace point program will fire. It may also take the it will call print k, which then takes that lock, and then that leads to a recursive execution. And then the kernel misses the execution of the second program. And so let's look at the second example here. It's a little bit simpler this time. We have a kprobe on open at 2, and in the middle of execution, an interrupt can fire. And the interrupt handler's code can also call open at 2, and then boom, you have a recursion there. So, and this is actually very common and very likely to happen, especially with file open events. It happens quite frequently on any normal machine. Both of these examples were generated on my own local machine without doing anything special. Now you can imagine how the performance of different hook points that we talked about earlier can have an impact here in terms of misses. So let's look at how specifically kprobes can miss executions next. So kprobe execution misses happen at 2 different layers. The first is the handler or the attached layer. At this layer, your kprobe program is set up to be executed. And at this layer, the kprobe specific recursion logic is performed, and it checks whether there is a kprobe running on the same CPU, basically. And the other layer is the actual BPF program execution layer, where your program executes as the JITted instructions. So at this layer, the BPF program's mutual exclusion on execution is handled, and that checks whether there's only one BPF program executing on the same CPU at a time. Okay, so let's dig into specifically the handler and the attached layer. So for kprobes, we have 3 handlers depending on your kernel config and kernel version. We have the standard int3 breakpoint handler. We have the ftrace handler, and then we have the optimized handler. Nowadays, running optimized kprobes, as seen in the table here, is the most common, but the int3 handler still exists for legacy purposes. Okay, and let's look at how these 3 handlers all have the same check. So they all do the same check for checking if the kprobes are running on the same CPU. So you can see that they check the current kprobe variable. This is very similar to the current task variable, if you're familiar, that holds like the current process running. And yeah, so if the condition that it's checking is true, it misses the execution of the kprobe. Okay, so all of this, and like, why does this even happen? So from my understanding, the kernel drops the execution to prevent corrupting the state of the kprobe currently running, because kprobes are interrupt based. Like, the nature of them is that they're interrupt based, specifically in the int3 handler that we talked about. If that handler is ever deprecated in the future, in future kernel versions, it's possible that the kprobe running restriction could be lifted, and that could reduce the amount of missed executions for kprobes. But for now, that logic still exists. Okay, and now let's move to the second layer where misses can happen. So we're past the handler layer now, and that means that there's no kprobe detected running on the same CPU. So at this layer, we have a check for a per CPU variable called BPF prog active. This check tells us whether there's already a BPF program running on the same CPU. So again, why does this even exist? It exists because it's to protect the per CPU kernel state that BPF programs might access or modify as they execute. So that's why if there's a recursion that happens, the kernel drops the execution of the second program to prevent that state from being corrupted. So without that, the nested execution would overwrite the existing kernel state. Okay, so now let's look at fprobes. So fprobes, unsurprisingly, do not use the kprobe running check, but instead they have their own check called the ftrace test recursion try-lock, and this happens in the handler layer. This function, in contrast to kprobes, supports one level of fprobe execution, nested fprobe execution on the same CPU, as long as that nesting happens in the same execution context like IRQ or process context. So here we can see that if you have an execution of the same fprobe in IRQ context and then the NMI context, it's not allowed. But if you have the same fprobe on the same CPU and in the same execution context, like both of them are IRQ, then this is actually a supported recursion. Okay. So again, in contrast to kprobes, fprobes use the BPF trampoline, and they're not interrupt-based. So at the BPF execution layer, this checks if the same program is already executing on the same CPU, and it's a per program variable here called under the struct prog active. And this counter is specific to an individual BPF program instance. So, but why is it only the same program? This is because fprobes are BPF trampoline based, which means each fprobe program has its own trampoline which stores its own state. So therefore, if a nested execution or recursion of the same program occurs, it would collide with the internal state of the initially running fprobe. So here's a quick summary of fprobes and kprobes that we just discussed. We focused on them here because they have the most interesting behavior to understand. Other hook point types such as raw trace points and raw trace points, perf events are very similar to kprobes and fprobes, but with some few small differences. Okay, so what is the solution to all of this? So if possible, if you can convert your hook point, your fprobe or your kprobe, to the equivalent BPF LSM hook, that would be the best case scenario. So for example, if your hook point is on file open events, you could find the equivalent BPF LSM hook, and in this case, it would be file open or file post open. And why LSM hooks? Because they're guaranteed to run even under the NMI context with concurrent executions, with recursion. And this is unlike the tracepoint BPF programs that we just talked about, because LSM hooks themselves are a different type of BPF program, so they don't have the same constraints of the tracing programs. So if you cannot use the BPF LSM hooks, then your best alternative is to use the tracepoint, because it has the least overhead that we talked about in the performance slide. So this is relevant because basically the least amount of time that the hook needs to run means that there is a less chance of interrupts that can occur on the CPU, and therefore reduce the window of recursion or a nested execution that would lead to a miss. Okay, and here's just like a quick summary slide that goes over the different details here just for reference. And now we'll go to the key takeaways. So under the generic category, we have for the performance reasons, try to use trace points as much as possible. If you're dealing with different kernel versions, use BTF and core if possible. And if you're dealing with different architectures, use fprobes or trace points, but not raw trace points instead of kprobes, and try to leverage the libbpf helpers as much as possible.
We've seen regarding kprobe and uprobe on dynamic links that the library, if the library are updated, the offsets are going to change and your probe can break silently. So you should reattach to probes after library updates or use trace points again. Regarding selective inlining, we saw that the symbol exists, but some call site are inline. So the solution is to trace the caller function or use offset. For partial inlining, you compiler splits function into fast and slow path, missing probes. So the solution can be using kprobe, prompt the different part suffix function, and for uprobe, you can compile with no partial inlining.
Yeah, and for missed executions, kprobes, they cannot recurse, so use optimized kprobes where possible if you really need to use them. Otherwise, prefer fprobes or even more preferably trace points. For fprobes and trace points, they have limited recursion support. So, and for kprobes, fprobes, and trace points, if at all possible, consider using BPF LSM instead. All right, and that's it. Thanks, everyone, for listening, and I hope this was useful. And thanks to everyone who also helped out with this talk as well.
Yeah, thank you so much. As mentioned at the beginning, we learned a ton while doing this talk. So there are a lot of references to articles, to talks from LPC, Linux Member Conference, especially, and we actually reached out to isovalent community with amazing eBPF people. And as you can see, there were a lot of responses, but that was actually very interesting. I wanted to mention one thing is that about the compilation optimization. So when we were exploring that topic while preparing, we saw that there is a bunch of compilation optimization that can actually make you miss some props. So this is only like 2 of them here, but there are many, many of them. And there is one Jerry's talk about it that was more exhaustive in case you want to go into that. So yeah. Do you have like anything you want to share like about preparing this talk? Like one thing that strike out or that you would remember or that is useful now for you as a developer? Okay, you can answer that, people. Yeah, Chris, tell me.
I think the most surprising thing for me was how much the hook points can miss.
Mm.
As I mentioned in the talk, in the slides, it just under a normal workload, just opening files. I mean, a hook point on file opens, you see thousands of misses that can happen within a few minutes, which was really surprising to learn. So I can imagine that in production, this can be a problem for sure.
Yeah, definitely. Okay, I hope that, in fact, yeah, it was useful. We were very happy to give this talk at the eCHO podcast today. And again, if you have any question, you can drop them in the Slack. And I hope to see you soon. Don't forget, next episode is with Duffy. So it's going to be very fun with AI Lab. So have a good day. Bye.